More examples. Both are longer. This one isn't that different than the last example. However, we're looking at 4 identical little spheres, whatever they may be, and they all have the same magnitude of charge, 5 microcoulombs, but they it says that the charge on the diagonals of the square, bottom left and top right, are negative, bottom left and top right are negative, and the other 2 are positive. Okay, so I've labeled my A, B, C, and D, and I want to find the net force acting on A here. This is what I'm looking for, the net force on A. So this one gets fun, and we might start asking the question. Maybe before we start, we could predict, what we expect. We know that A would move, this way due to B, would move down toward due to C, but due to D, it would move off on an angle like this, right? It moves totally straight away from it. And the question is, well, what's the end result then? I'll let you predict. But here's the information that we are given. We're given the 4, I guess, charges. And C and B here are negative, and those 2 are positives, the only difference. We know the distances, because it's 25 centimeters on the sides of the square. And then we need to know the distance between A and D, and that I applied Pythagorean theorem. Right, here's a right angle triangle. So applied Pythagorean theorem to find RAD it's probably approximately 0.354. I'm guessing I rounded to get that. Okay, so I kind of have all the detail that I need, but what you can imagine is we're going to have to do things in the X direction and in the Y direction. I only know 5 things, I just know them really well, right? And this is one of them. Okay, so this is what I was just talking about. It's going to end up moving on an angle, so we're going to find X and Y components, right? Here's sort of my picture saying, due to B, it'd be that way, due to C, it'd be that way, and those should be the same magnitude, and due to AD, it actually should be a little bit less due to D, because it's a further distance here. So this one should be a little smaller in magnitude. These 2 should be the same, and that one should be a bit smaller. 45 degrees because this is a right angle triangle, and all the sides, this side and that side, are the same, so it's isosceles, so it's 90. Okay, 45 degrees. So we want to find the net force of these 3 things. And, there's different ways you can do that, but I'm going to use X and Y components. So I'm calling down and to the right positive for this particular case. So I say, okay, in the Y direction, the net force on A in the Y direction will be, it's due to AB in the Y direction, which will end up being 0, right? AC in the Y direction, and AD in the Y direction. It would be sort of like the vertical component of this, right? If I was going to draw little components in there, I'll use this one. I could draw little components and say, there's the FADY, and here's the FADX, right? So, first of all, this one is 0. It's just a horizontal force. I threw my pluses and minus in here already. Let's just see why. AC, I've called right positive, so that's going to be all positive. And, I called down positive. So it's going to be just positive, right? Because this A will be attracted to C. Because A is repelled from D, it's the A, the FADY, FADY, is in the up direction. So it's going to be negative. Then you put in, the numbers for these. It's sine 45. Well, it's because it's, like I just drew here, it's opposite that 45 degrees. Okay, so that's where all that came from. Solve for FAY, just substitute in the numbers and solve. Well, here I drew the vector right there too. Yeah, do the same thing in the X direction. Exactly the same thing. And it's the same, okay, which probably makes sense because everything sort of cancels out. So now I know they're both positive. They're both what I call positive. So my net force is going to be in the positive, like in this direction here. on a 45-degree angle, and I say 45 because these are the same magnitude, right? So I can solve for FA, right? 3.3 newtons. And I know I didn't have to, I decided not to bother using, tangent to find 45, because if these are both the same size, it's an isosceles triangle. So if this is right angled, which of course it is, they both have to be 45. So I can just say my answer. Okay, so that's a tough one. It's a big, long question, and it is important, definitely important to understand this one as well. Okay, this one, the last example on Coulomb's law, is really important to understand because this is similar, not exactly the same, but very similar to your lab. Okay, so you're actually going to do this with the little pith balls. This is the lab for this. Got little pith balls. It's hard to, I'll be honest and say, it's hard to get a really good result, but you fake it a bit for me and get and have a nice lab. But basically, you charge 2 pith balls, right? And they're going to move apart from each other. Now, in this particular example, this one is held straight for some reason. So this one is held in position for some reason. It's not allowed to move. In your pith ball example, they sort of move off on, this one would move away and they'd be separated by a little angle. It's a really small angle, by the way. But in the lab, or in the question, this is the scenario. We have a 12-degree angle. B is straight down. A is off here. So we know the length of the wire. This is 2 meters right here. And this one's held here. This one's moved 12 degrees away. And what's going on is the electric repulsion between B and A causes them to sphere A to overcome gravity, right? It should want to just fall into B, right? But it won't because of this electric force. So really, we have a balance where there's gravity and an electric force working together. And we have a system in static equilibrium. They're just being held there. They're not moving, right? The electric force between them is causing this angle to exist. So what do? We could do a free body diagram, and we're going to come up with equations using the free body diagram and static equilibrium to solve for the charge, because that's what we're looking for. We want to know the charge here. By the way, here's another little piece. If these two come into contact, okay, what you can always assume happens is that, see, it says that A was neutral to begin. Well, if they come into contact, you can assume that, say B, for the sake of argument, was initially 2 coulombs. Well, after they touch, you can assume they each have 1 coulomb, that it gets split evenly. We don't know what the number is. That's what we're solving for. But you can assume that they have the same charge, wherever that charge is. So here's my free body diagram on on A. And what I'm saying is there's tension. This is the tension, and here's the picture of the little wire holding it, or little string holding it, and there's tension in that string. And you're looking at the forces acting on my sphere A here. Well, there's the tension, which has an X and Y component, and there's electric force pushing it away, right? Pushing it away from B, and there's gravity pulling down. So we must know the mass, we must know the mass, okay? So there's my free body diagram, and the things that I can figure out, I can use the Y direction and figure out the Y component of my tension, right? Because my Y component of my tension will be equal to gravity. So this number here is going to be equal to 0.98 newtons. Now when I do my X direction force balance, I can say, well, left equals right. So Ft(x) will be equal to electric force, which is going to be equal to our 2 charges. But we said that the charges were equal, right? They're just Q. We said that they had to be equal. So we're solving for Q is what we're looking for. So we say Ft(x) equals kq squared over r squared. The problem is we don't know this, we don't know q, and we don't know r. At least we know k is 9 times 10 to the 9. We know that much, right? So, let's see what we're going to do. We do know Fty, and that's going to help us, right? Because we know Fty and we know 12-degree angle. So that's going to allow us to find FTX. So once we know FTX, we can also find out R because of the geometry of the situation. So when you do your lab, you can actually just measure it. But this is just me, the purple print is just me talking about the fact that each charge is the same and they're half of the original and all that. But figuring out R, right, so here's my situation. I got a 2 meter long string. I got a 12-degree angle, and I want to find out R because that's the distance between the two spheres. So you can say, well, R over this, right, R is like the opposite to the 12 degrees, equals sine 12. So R equals 2 sine 12. So we could figure out that as a number. I'm just going to leave it as 2 sine 12 actually instead of rounding. The longer you can wait to round, the better your answer is. When finding out FTX, I can say, okay, well, I know this is 0.98 on my free body diagram. This is FTX. This is 12 degrees, so kind of the same idea. Now I know 0.98 is like the adjacent to the 12 degrees. So FTX, which is opposite over adjacent, equals tan 12, so I can solve for FTX. This stuff is hard, right? There's no question about it. It's really hard stuff. But we do now have FTX. We now know R, so we can actually solve for Q now. Because this is the equation I have. I know FTX and I know R, right? Solving for Q, and I get a number. So Q is, now this is after they come into contact. And I think we must have been given that they were negative. And so we can say the original charge on B must be twice that, right? Because it gave half of its charge to A, and it's got to be, and we're told that it's negative, so Q, the original Q then is a negative charge. Now, how do I know it's a good answer? I don't really, except for one thing I've mentioned before, is that charge is normally in the order of times 10 to the negative 6. When you do your lab, it's less than. I think you're going to get something like times 10 to the negative 9 or 8. Okay, you get a much smaller number in the lab, but in our questions, they're typically times 10 to the negative 6. So that's a reasonable number, okay, for us. Okay, that was a really tough example. And again, star it. I think there's one like this in your problem set, but star it. You need to be able to reproduce this for sure. It could come up on a test.